There's one other nice way of solving the types of problems we've been looking at, and this is sometimes known as the method of direct integration. And it's a technique that allows you to solve both determinate and indeterminate problems using the same methodology. So there's a bit of utility to it in that you only have to sort of know one way of doing the problem, and you can solve both determinate and indeterminate problems. And what direct integration relies on is solving the equilibrium equation as a differential equation. So far when we've been looking at the question of equilibrium and the problems we've treated, we've used free body diagrams to determine what the internal forces are. But one can actually solve the differential equation that governs the internal force, which is dr dx plus b equals 0. And one can integrate this equation and come to a solution also. And it kind of is a nice way of doing problems. Now when we do this, we don't actually solve this equation directly in terms of r. We do this indirectly in a way is that we convert this equilibrium equation for the internal force into an equilibrium equation in terms of the displacement field. And then we solve first for the displacement field. Knowing the displacement field, we can easily back calculate all the other quantities, strains, stresses, and internal forces. So the way we do this is first, we substitute in the relationship between the stresses and the internal forces into the problem. So we go ahead and say that the internal force R is equal to stress times the area. So we just stick that in there. And now what we're going to do is we'll substitute out the stresses in terms of the strains. So that's replacing sigma by epsilon times E, the Young's modulus. And then lastly, we'll go ahead and substitute out the strain in terms of the displacements. So we'll replace the strain with du dx. And that leaves us with a second order ordinary differential equation for the displacements that has to be solved. Now, if AE happens to be a constant, I can pull it out from inside that inner derivative, and I have this slightly simpler looking equation, AE, two derivatives of u plus b equals 0. And so this is a second order ordinary differential equation with constant coefficients. To solve these types of equations, you need two boundary conditions. You typically take one from the left side of the bar and one from the right side of the bar, so one at x equals L and one at x equals 0. And those two conditions allow you to solve for the two constants of integration that you'll get when you integrate the second order ODE. The common boundary conditions that we deal with are the cases of known displacement. So perhaps you know the displacement at x equals 0, or you know the displacement at x equals L, and that's a given number. If it's a built-in end, it would be 0, but you could actually have an imposed displacement also. And then the other common boundary condition is a known force. So suppose there's a force applied at one end of the bar. And in that case, what you actually know is the combination of terms AE du dx. And if you look at this carefully, you'll see what's going on here. Du dx is a strain, and E is a modulus, so E times du dx is a stress, and A is an area, so stress times area gives you force. So this is a way of writing down a known force. You can say I have a known force value, it's equal to AE du dx at that point. And that's a condition, and you can use that condition then to solve for the constants of integration that occur when you integrate the second order ODE. And it's a nice way of doing it. You combine all the equations together into a single equation. It's an equilibrium equation, and it's an equilibrium equation in terms of the displacements. Once you've solved for the displacements, it's easy to go back and compute the strains because it's just a derivative. You can then compute the stresses by multiplying by the modulus, and you can compute the internal forces then just simply by multiplying by the cross-sectional area.